So right now, just sitting there, you probably feel pretty solid, right? I mean, the chair beneath you feels solid. The device you're listening to this on, it feels completely tangible.
Oh, absolutely, yeah.
But according to literally the most successful scientific theory in human history, you are mostly empty space,
Yeah.
just like held together by this raging microscopic storm of invisible ghost particles, basically throwing tiny subatomic balls at each other millions of times a second.
It really shatters your entire perception of reality when you really look at it, doesn't it? I mean, for most of human history, if you asked a philosopher or even a scientist what reality was fundamentally made of, the most honest answer they could give you was simply, nobody knows.
Right, it was just a giant mystery.
Exactly. But that is not the answer anymore. Today, physicists actually have an answer, and it is remarkably, almost unnervingly precise.
Which is exactly what we're getting into today.
Yeah.
We are taking a deep dive into what humanity has painstakingly assembled over, really, the last century.
Yeah.
It's the universe's ultimate ingredient list.
Yeah, it's basically a master catalog of the most basic building blocks of absolutely everything around you. And importantly, the invisible forces that dictate how all those blocks behave.
And this list has a very specific name, right?
It does. It's known as the Standard Model of Particle Physics.
Hmm.
And it occupies this incredibly unique, almost paradoxical space in science because, on one hand, it is universally considered one of the absolute crowning achievements of the human mind. I mean, the mathematical precision is staggering.
Right, it's predicted things way before we found them.
Yes, decades before we had the technology to actually find them in a lab. But on the other hand, it is a theory that physicists openly and often with immense frustration, I should add, describe as totally incomplete.
Okay, let's unpack this.
Yeah.
Because if you hear the phrase, particle physics, and your brain immediately signals you to just run for the hills, do not worry.
Yeah, stick with us.
Exactly. We are going to take our time. Together, we're going to assemble the universe from scratch, piece by piece, right here, right now, without needing like a whiteboard full of crazy equations.
I think of it like, well, imagine deconstructing a master chef's signature dish. You simply cannot understand the complexity of the meal without first looking at the raw ingredients sitting on the counter.
That makes total sense.
So if we want to know what everyday matter actually is, you, the listener, the device playing this audio, the stars burning in the night sky, we really have to look at the absolute smallest uncuttable pieces it's built from.
Right. And according to this standard model, all of that physical matter, the tangible stuff, comes in two distinct families. So let's start with the first family, the one that handles, I guess, the heavy lifting, the quarks.
Yes, the quarks. So we all kind of learn in school that atoms have this dense central nucleus, right? Made up of protons and neutrons.
Right, the classic atom diagram.
Exactly. But the standard model goes deeper. It literally cracks that nucleus wide open. Protons and neutrons are actually not fundamental at all.
Wait, they aren't?
No, they're composed of even smaller particles glued together. And those are the quarks. It takes exactly 3 quarks to build a proton and 3 to build a neutron.
And physicists, being who they are, gave these quarks some incredibly playful names. And there were 6 types of quarks on the menu, and they're called up, down, charm, strange, top, and bottom.
Which tells you a lot about the sense of humor in the particle physics community.
It really does. It sounds like a minimalist poem or something. But the crucial takeaway for you and me here is that even though there are 6 of them available for everyday matter, only 2 of them are actually used.
That's right, just 2.
The up quark and the down quark. Like if you combine 2 up quarks and 1 down quark, you get a proton.
Yep.
2 downs and an up, you get a neutron. And that is it. Nearly all the physical substance of the visible universe is built from just up and down quarks.
It's amazing. Which smoothly brings us to the second family of basic ingredients, which are the leptons. And the most famous member of this family is undeniably the electron.
Oh, okay. So the electron is a lepton.
Yes, it's that tiny, negatively charged particle that swarms around the outside of the atomic nucleus, and it's the exact same particle surging through the wires of your house right now to provide electricity.
Okay, so if the electron is a lepton, what else is in that family? Are there others?
There are. The electron has a couple of much heavier, highly unstable cousins, but it also has these bizarre, almost ghost-like companions called neutrinos.
Oh, man. The neutrinos are wild. Let's spend a second here because this stat completely blew my mind when I read it.
They are wild. They are essentially massless. They have absolutely no electric charge, and they stream through the universe in just unfathomable numbers.
Because they don't have a charge, right? So they don't hit anything.
Exactly. They barely interact with normal matter at all. To put this in perspective for you, Trillions of neutrinos. Trillions produced by the nuclear furnace of the sun are passing through your body right now, every single second, without colliding with a single atom inside of you.
Trillions every second, just passing straight through the Earth and out the other side like a ghost passing through a wall. It's crazy.
It really is.
But zooming out to look at like the whole pantry here. Together, the quarks and the leptons make up all the matter particles, 12 of them in total. And they're arranged in 3 sort of generations of increasing mass.
And here we really see how ruthlessly economical nature is. The universe has 12 matter particles to play with, but everything's stable and familiar. Everything we see, touch, and breathe uses only the lightest generation.
Which is the up quark, the down quark, and the electron.
Exactly. Plus the neutrino just sort of floating around in the background.
You know, instead of just thinking of this as a box of different sized Lego bricks,
Yeah.
I kind of like to think of everyday matter as a minimalist cover band.
Oh, I like that.
Yeah, so the universe has this massive, chaotic 12-piece orchestra available to it. But for everyday reality, it only hires a 3-piece band. You got the up quark on drums, the down quark on bass, and the electron on vocals.
That's perfect.
Right. Those 3 create all the music we actually experience. The heavier particles, the rest of the orchestra, they definitely exist, but they only ever show up to play in like extreme high energy environments, like the hearts of exploding supernovas or in our particle accelerators, and then they just decay and vanish almost instantly.
That is a really brilliant way to frame it. The universe relies entirely on the minimalist band for stability. But of course, just having a band on stage doesn't mean they're actually playing music.
Right. A pile of ingredients just sitting on the counter is definitely not a universe.
No, it's not. They need to actually do something. They need to interact. They need forces to bind them together, to push them apart, to make them move.
Okay, so how does that work in this model?
Well, this is where the standard model pivots from just listing ingredients to doing something truly profound. It doesn't just treat a force as some mystical, invisible wave. It dictates that forces are actually carried by their own special particles. We call them bosons.
Okay, wait. I want to make sure we really grasp the mechanics here. How can a force, like a literal push or a pull, be a tiny physical particle?
Okay, so imagine 2 ice skaters standing perfectly still on a frozen rink, facing each other. One of them is holding a heavy medicine ball. Now they throw the ball to the other skater. The physical act of throwing that heavy ball pushes the first skater backward.
Oh, because of the recoil.
Exactly. And when the second skater catches it, the impact of the catch pushes them backward too.
So they basically push each other apart without ever actually touching each other, purely through the conservation of momentum.
Yes. In a quantum sense, that is the literal mechanism of nature's fundamental forces. Matter particles are throwing microscopic force particles back and forth between them. The continuous act of exchanging those messenger particles is what actually generates the force.
Wait, let me push back on this for a second, just to be absolutely clear.
Yeah.
So when I take a magnet, right, and I stick it to the door of my fridge, it's not just some invisible continuous field of magical energy pushing it toward the metal. Nope. It is actually a physical exchange. Like tiny particles are literally being thrown back and forth between the magnet and the fridge.
What's fascinating here is that exactly what you described is true. That smooth, continuous magnetic pull you feel in your hand, it's actually an unimaginably dense, rapid-fire flurry of microscopic particle exchanges.
That is insane.
It is beautifully counterintuitive. It feels like a smooth wave to us, but it's made of trillions of tiny, discrete impacts.
Mind-blowing. Okay, so what are the specific messenger particles throwing these forces around then?
So the standard model outlines 3 fundamental forces, each with its own specific carrier. First, you have the electromagnetic force. This force dictates light, electricity, magnetism, and actually the very solidity of matter itself.
Like solidity, like touching things.
Yeah. The reason your hand doesn't pass right through the table is because the electrons in your hand are exchanging force particles with the electrons in the table, repelling each other. And the particle they are throwing back and forth to create that repulsion is the photon. The photon is the particle of light.
Wow. So light, a fridge magnet, and the literal reason I don't fall through the floor are all fundamentally driven by particles playing catch with photons. Incredible.
It really ties it all together.
But, okay, if photons handle the electric push and pull, what keeps the atomic nucleus itself together? Because if I remember right from science class, protons all have a positive charge. And like charges repel. Shouldn't a densely packed cluster of positive protons just violently blow itself apart?
It absolutely should. The electromagnetic repulsion pushing those protons apart is immense, which means there must be an even stronger force overcoming it, actively binding the nucleus together.
Okay, that makes sense.
This is creatively named the strong force. It operates exclusively at microscopic subatomic distances, but is immensely powerful. It literally glues the up and down quarks together inside the protons and then holds those protons together in the nucleus.
And what particle carries the strong force? Let me guess. The names are going to get weird again.
Actually, it is very literal this time. The particles carrying the strong force are called gluons.
Gluons. Just literally glue particles. I mean, I suppose we can't fault them for clarity there.
It's very descriptive.
So we have electromagnetism and the strong force. What is the third one?
The third is the weak force. The name sounds underwhelming, but its mechanism is arguably the most bizarre of them all. It is responsible for certain types of radioactive decay, and critically, it drives the nuclear fusion reactions that allow the sun to ignite and shine.
Oh, wow.
Yeah, and the weak force is carried by incredibly heavy messenger particles called the W and Z bosons.
But how does a force particle actually cause something to decay? Because when I think of radioactive decay, I think of like an atom breaking down.
Right, but the W and Z bosons don't just push or pull like the others. When a quark emits or absorbs a W boson, it actually changes its fundamental identity. It basically commits subatomic identity theft.
Identity theft.
Yeah, an up quark can throw a W boson and instantly transform into a down quark.
Whoa. So it's like a pitcher throwing a baseball, and the sheer act of throwing the ball magically transforms the pitcher into a tennis player.
That is exactly the scale of the weirdness we're talking about. And when that quark changes its flavor, the entire proton it was part of turns into a neutron. That fundamental shift in the atom's identity is the literal mechanism of radioactive decay. The weak force alters the very nature of the particles it touches.
Okay, so we just listed three forces: electromagnetism, the strong force, and the weak force.
Correct.
But I'm looking around the room right now, and there's a glaring elephant sitting right here. Everyday life clearly features a fourth force.
Ah.
It's the one currently holding us down in our chairs so we don't float into the ceiling. Where on earth is gravity in this model?
And here we arrive at the first great embarrassment of the standard model. Gravity is simply not in it. It is completely, totally missing.
Wait, really? The most meticulously tested, mathematically successful theory in the history of human civilization just forgot gravity.
Well, it didn't forget. It just fundamentally cannot make the math fit. I mean, the standard model describes the behavior of quantum particles with breathtaking 12 decimal point accuracy, but it has absolutely zero working description of gravity at that microscopic level.
That is wild. It's like writing the ultimate, flawlessly accurate rulebook for the game of baseball, mapping out the exact physics of the bat and the grass and the wind, but completely forgetting to include the ball itself.
Yeah, that's a pretty fair comparison.
How do physicists deal with gravity, then, if it's not in the model?
Gravity is handled by an entirely separate and equally magnificent theory, which is Albert Einstein's general relativity. Einstein described gravity not as particles being thrown back and forth, but as the smooth, continuous bending and warping of space and time itself.
Right, the whole fabric of space thing.
Exactly. Massive objects curve space, and other objects fall into those curves.
So relativity says reality is this smooth, continuous trampoline, and the standard model says reality is a chaotic, chunky storm of microscopic particles throwing things at each other.
That is the absolute core of the crisis. These two frameworks, the smooth geometry of general relativity for the cosmos and the chunky, jittery particle exchanges of the standard model for the quantum world, they stubbornly refuse to merge.
They just don't work together.
Not at all. When you try to combine their equations to describe something that is both incredibly massive and incredibly tiny, like the center of a black hole or the exact instant of the Big Bang, the math just produces infinity. It breaks down completely. Reconciling these two theories into one theory of quantum gravity remains the absolute holy grail of modern physics.
So there's a massive hole in the theory. But before we dive into the other things the model gets wrong, there's one more crucial piece of the puzzle we do actually have. Because speaking of gravity and, well, things being heavy, why do any of these particles have mass to begin with?
That is the million-dollar question.
Right. Why does an electron weigh almost nothing, but a top quark is incredibly heavy?
And this brings us to the absolute celebrity of the particle physics world, the particle that literally made global headlines, the Higgs boson.
Here's where it gets really interesting.
It does. So the Higgs mechanism was predicted mathematically back in the 1960s by Peter Higgs and several others. The math demanded that it exist, but it wasn't actually confirmed in reality until 2012.
Wow, that's a huge gap.
Huge. Thousands of scientists finally detected it using the Large Hadron Collider in Switzerland. It literally took 50 years of obsessive searching to find it.
50 years of building bigger and bigger underground machines just to find this one missing puzzle piece. But what does the Higgs actually do? Like, why is it so important?
The Higgs solves that profound mechanism you just asked about, how matter acquires mass. The concept is that all of space, everywhere in the entire universe, is permeated by an invisible underlying energy field. We call it the Higgs field.
Okay.
You can conceptualize it like a cosmic ocean that fills a seemingly empty room just as completely as it fills the vacuum of deep space.
Okay, I'm picturing this invisible, inescapable ocean everywhere.
Right. Now, as fundamental particles move through this field, they interact with it. And that interaction generates drag. It creates resistance. And that resistance is the very mechanism that you and I experience as mass.
Ah, okay, so it's a drag effect.
Right.
Like if you try to run on dry sand, it's pretty easy. But if you walk into the ocean and try to sprint through waist-deep water, it is exhausting. The water actively pushes back. It takes real effort to accelerate.
That is the mechanism entirely. Particles that interact strongly with this Higgs field feel a massive amount of drag. They are the heavy particles, like the top quark. Particles that interact weakly with the field feel very little drag. So they are the lightweight particles, like the electron.
Okay, but what about the photon, the particle of light? Because light travels at the ultimate speed limit of the universe, right?
The photon is uniquely special. It does not interact with the Higgs field at all.
Not at all.
None. It slips right through without causing a single ripple. And because it experiences zero interaction, it experiences zero drag, which means it has precisely zero mass. And because it's massless, it is fundamentally obligated to travel at the absolute speed limit of the cosmos, the speed of light.
That is such a vivid image. So the heavy particles are constantly trudging through this waist-deep water, struggling to move. The light particles are swimming pretty smoothly. And the photons are just flying freely through the air right over the surface of the water, completely untouched.
Exactly. It's a beautiful way to visualize it.
But wait, if the ocean is completely invisible, how did the Large Hadron Collider actually find it?
Honestly, by using sheer brute force.
Really?
Yeah. The Large Hadron Collider accelerates protons to 99.999% the speed of light and basically smashes them into each other head-on. The mechanism is like taking two incredibly complex Swiss watches, firing them at each other from cannons, and then studying the gears that pop out of the explosion to figure out how time works.
That sounds incredibly chaotic and really expensive.
It is both. But in that extreme, concentrated flash of energy, the impact actually strikes the invisible Higgs field hard enough to knock a temporary ripple out of it. And that physical ripple, that concentrated droplet of the ocean, is the Higgs boson particle.
Oh, wow.
It decays almost instantly, but by detecting the gears left behind, physicists proved the invisible ocean was really there. Finding it in 2012 completed the standard model. It slotted in the very last predicted piece, completely validating half a century of theoretical math.
So the final piece of the puzzle is found. The rule book is officially complete. Do physicists just pack up their briefcases, turn off the lights at the collider, and go home?
Far from it. If we connect this to the bigger picture, you can ask literally any particle physicist working today, and they will excitedly be the first to tell you that the standard model simply cannot be the whole story.
Because of the missing gravity problem we just talked about.
That is a massive part of it, yes, but it's also because of the sheer volume of reality it completely ignores. The list of blind spots is just staggering. For instance, the standard model offers absolutely no explanation for dark matter.
Which is a pretty big deal.
It is an astronomical deal. We look at galaxies spinning in space, and based on the gravity of the visible stars, those galaxies are spinning so fast they should literally rip themselves apart and scatter into the void.
But they don't.
Right. The only way they stay glued together is if there is a massive halo of invisible matter providing extra gravity. This dark matter literally outweighs ordinary visible matter 5-to-1 across the universe. We can see its gravitational fingerprint everywhere, but the standard model has no particle for it. It's totally blind to it.
So the model perfectly describes the cherry on top, but it totally ignores the actual cake.
It gets worse. It also has absolutely nothing to say about dark energy, which is the mysterious force that is actively accelerating the expansion of the universe, stretching space itself apart.
So it's missing gravity, dark matter, A and D dark energy.
And, perhaps most existentially, it cannot explain why there is more matter than antimatter in the universe.
Wait, what do you mean?
Well, according to the foundational equations of quantum mechanics, the Big Bang should have created perfectly equal amounts of both matter and antimatter.
But matter and antimatter violently destroy each other when they touch.
Precisely. If the universe had been perfectly balanced, every single particle would have instantly found its antimatter twin and annihilated it in the first fraction of a second.
Wow.
The universe would just be an empty, expanding sea of cold radiation. Nothing physical would exist. The sheer fact that you and I are here having this conversation means there was an incredibly slight imbalance.
Really?
Yes. For every billion antimatter particles, there was 1,000,001 matter particles. We, the stars of the planets, we are literally the leftovers of a cosmic accounting error. And the Standard Model cannot tell us why that error happened.
Okay, that is an incredible aha moment. We exist purely because of a microscopic rounding error at the dawn of time. That alone makes you realize just how fragile the model's grip on reality really is.
It does, and this raises an important question. What do we do when a theory is this undeniably successful, predicting reality to 12 decimal places, but clearly incomplete? Because there is one final quirk to the Standard Model that keeps theoretical physicists staring at the ceiling at 3 a.m. The mathematical model contains 19 fundamental numbers.
19 numbers. Like what? Like measurements.
Values like the exact mass of the electron, or the precise strength of the strong nuclear force, or the mass of the up quark.
Okay.
But the theory itself cannot predict what those numbers should be. They don't naturally arise from the mathematics. There is no equation in the Standard Model that says, the electron must weigh exactly this much.
So how do they know the numbers?
Scientists just have to physically measure the electron in a laboratory and then manually type that value into the equations by hand to make the model work.
Wait, I really need to push back on this. If we just have to invent numbers, measure them in a lab, and retroactively cram them into the math to make the equations balance, how is this different from just a math trick? Why do we trust this theory at all if it can't even predict its own fundamental variables?
That is the exact frustration physicists feel. To a physicist, having to plug numbers in manually by hand is a glaring neon sign that a deeper, more fundamental theory lies beneath this one. It's called the fine-tuning problem.
Right.
If you take the mass of the down quark and you artificially dial it up or down by just a tiny percentage, the protons and neutrons inside atoms would become unstable and fall apart. The universe would be entirely incapable of forming atoms. Stars would never ignite. The universe would be a dead, featureless void.
So those 19 numbers are perfectly tuned for life to exist, but the model has absolutely no idea why they are tuned that way.
It's like finding a master recipe for the universe, but 19 of the most vital steps just say, add a random amount of spice until the universe looks right. It works, but it fundamentally doesn't explain the underlying logic of why it works. There must be a deeper mathematical reason why the strong force is exactly as strong as it is. We just haven't found the math that explains the why yet.
So what does this all mean? I mean, we've sliced reality all the way down to the up quarks and the electrons. We've thrown force particles back and forth across the ice rink. We've trudged through the resistance of the Higgs Ocean, and we've peered into the terrifying voids of dark matter and missing gravity. Where does this actually leave us?
I think it leaves us with a profound truth about the nature of science itself. The Standard Model is not wrong. Within its very specific quantum domain, it is extraordinarily, unbelievably right. It has survived half a century of the most rigorous, aggressive experimental testing humans could possibly throw at it.
But being mathematically right is not the same thing as being complete.
Exactly. A truly great scientific theory is entirely honest about its own edges. The Standard Model tells us with staggering, triumphant precision what it knows, but by its silences, by remaining completely silent on gravity and dark matter and that beautiful antimatter accounting error, it points directly at what we still critically need to discover.
It's like an ancient explorer's map, right? It beautifully and accurately draws the known coastlines, but it also clearly marks the massive, terrifying empty oceans where the dragons are.
Yes. I love that analogy. And this is exactly why physicists are right now lobbying to build even bigger, vastly more expensive colliders and lowering unimaginably sensitive dark matter detectors deep underground in abandoned mines. They aren't trying to prove the standard model right anymore.
They're trying to find the dragons.
They are desperately trying to break the model. They are deliberately hunting for the first crack, the first unexpected particle, or the first strange decay behavior that the standard model absolutely cannot explain.
Because the moment they find that crack, that flaw in the armor, it becomes the doorway to whatever grander, deeper theory comes next.
Precisely. And I want to leave you with a final thought to sort of mull over.
Please do.
The next time you are sitting in your house, just take a moment to look around at the physical world. Look at the light emanating from a lamp. Feel the unyielding, solid ground under your feet. Look closely at your own hands. Think about the fact that every single bit of that, every sight, every touch, every interaction is built from a tiny, minimalist handful of fundamental particles performing a complex dance perfectly described by human mathematics.
It really is beautiful.
We actually figured that out. We cracked the code of our everyday reality. But then tonight, step outside and look up at the vast, empty night sky. And remember that for all of our breathtaking brilliance, the vast majority of the universe's true recipe is still completely invisible to us, just waiting in the dark to be discovered.
We've sliced the bread all the way down to the final uncuttable crumb, only to realize we've been staring at a single crumb this entire time. There is an entire bakery out there hidden in the dark waiting for us to find it. Well, thank you so much for joining us on this deep dive. Keep questioning the world, keep looking closely at the forces around you, and we will see you next time.